All right, so this is our quiz on geostationary orbit from May 14th, 2021. And it starts with state Newton's law of gravitation. You've seen that one before. Newton's law of gravitation states that the force of gravity between two point masses, oh, I forgot the word point, between 2 point masses is directly proportional to the product of the masses.
Isn't that what geostationary is?
Nope, I'm just stating Newton's law of gravitation right now. The force of gravity between 2 point masses is directly proportional to the product of the masses and inversely proportional to their separation distance squared. So that is to say the force of gravity directly proportional to the product of the two masses. The force of gravity is inversely proportional to how far apart they are squared. So if you have two masses, walk into a bar. Get it? Like a bar. Two masses walk into them. That's it. That's the whole joke. You're welcome. All right, separated by a distance r. Maybe you guys can't see that clear. Two masses walk into a bar, separated by a distance r, and the force of gravity between them is Gmm over r squared. So this is the equation to get sort of, you could put both of these ideas together, but to make it an equation, we need a constant of proportionality. So that constant is Newton's universal gravitational constant, capital G. So that's really the equation that captures this law. But to put it out in words, there you go. Now it says a geostationary satellite orbits the Earth. The orbit of the satellite is circular, and the period of the orbit is 24 hours. State two other features of this orbit. Anybody have one? Find it in your notes. Anybody? Two other features of a geostationary orbit. So because the Earth rotates from west to east, so too must geostationary satellites, right? They got to go in the same sort of direction that the Earth is orbiting. So the orbit is from west to east. And let's sort of make a follow-up note. Same direction as Earth's rotation. The goal is to keep the satellite over the same point. So giving it a period that is the same period as it takes the Earth to, spin on its axis ensures that the satellite will remain stationary over a single point above the Earth, right? So geostationary. So the orbit has to be from west to east in the same direction as Earth's rotation, and it has to be above the equator. The orbit has to be above the equator. It can't be sort of above the North or South Pole. If you think about, it's sort of the Earth at the equator, right? That goes around. So if we have a geostationary satellite that's sort of up here and the Earth is spinning this way, right? So we need it going around sort of above the equator at a great enough distance that it takes 24 hours. So at the same, as the Earth rotates, the satellite just sort of keeps going right along with it. All right. So those are two other features of the orbit. Anybody say anything else besides those two? Am I missing? There could be others, I suppose. Yeah, I mean, this is really key right here. The period is 24 hours. They already give you that. So those are two other ones I could think of. We'll check the March scheme. It says the radius of the orbit of the satellite is 4.23 by 10 to the 4 kilometers. Determine a value for the mass of the Earth. Explain your working. Well, there's probably a good reason to start with Newton's law of universal gravitation. We're going to need that. So we got two masses. We got a satellite and we got the Earth. Okay, so let's kind of start with that. Force of gravity is G(m)(m) over r squared. And we're going to solve for the mass of the Earth, right? So the Earth is the thing being orbited. So we just have to kind of think about, all these ideas that we've talked about previously. The force that keeps the satellite in the circular orbit is the centripetal force, provided by gravity. But that in general is equal to mass times velocity squared over r. And we know that velocity around a circle, velocity in general, distance divided by time, but around a circle, 2 pi r, here we have r, the radius of the orbit. So they don't give us like an extra calculation to add in the height above the surface of the Earth. It's just, here's how far it is from the center of the Earth, the radius of the orbit. Over t, we also know that t, so r is this in kilometers, and t is 24 hours. The units of both of these are no good for our purposes, right? Because g is metric units, right? So we need this to be in meters, we need this to be in seconds. So let's take care of this one first. R is 4.23 by 10 to the 4 by 10 to the 3 meters. So this kilo means 10 to the 3 means 1,000. So it's already 10,000 meters. So we can just combine those together and call that 4.23 by 10 to the 7 meters, right? See that? It's just an extra 3 orders of magnitude. And the rules for exponents are to add them, right? If you're multiplying two exponents like this, you add the exponents. So we got that. That's what r is equal to. 24 hours times 60 minutes per hour times 60 seconds per minute. 86,400 seconds per day per 24 hours, right? So that's what we want there. We're gonna have to use this to solve for m. Let's first equate these two for the first time ever this year. Oh wait, no, we've done this hundreds of times. So we'll cross out those, cross out that one. And now we've got the famous orbital velocity equation. And we'll substitute in for v because we know r and t, right? So it's like v, we have to put that in terms of what we know. So if we plug in 2 pi r over t for v, we got to square it, right? V squared equals gm over r. We write this up here. 2 squared is 4, pi squared is pi squared, r squared over t squared on the left side equal to gm over r on the right. If I multiply both sides by r over g, then I get the mass equal to, right? Cancel out those g's, cancel out r, so m all by itself equal to all this. That's 4 pi squared r cubed, right? R squared times this r cubed over g t squared. R cubed over t squared. Pop quiz. Which law is that? That r cubed and t squared are in proportion. Call it out if you know it. You learners, say it again. Kepler's law. Which one? Which one? You learners, you can steal. You can steal right now. Hurry up. Call it out. Unmute your mic. Everybody in class is like, I got it in my notes. Who's gonna get it? Come on, you learners. I got high hopes for you. Kepler's which law of planetary motion? R cubed over t squared. Like the students, it's like there is a penalty for an incorrect yes. So like they're very careful right now. It's like, oh no, yeah, but it's oh no, I can't. No corporal punishment.
I can't find it in my notes.
All right, can't find it in the notes. Anybody have it in their notes there? R cubed over T squared. How many laws of planetary motion did Kepler have? It is the third. Very good. Kepler's third law of planetary motion says that R cubed over T squared are in proportion. So you notice that empirically from the planets that the distance that planets were from the sun cubed was in proportion to how long it took them to orbit the sun squared. And we see that here. Now I just got to substitute in some values. So I'm going to do that over here. M equals 4 pi squared times. Now R we said was 4.23 by 10 to the 7 meters cubed over. G is 6.67 by 10 to the minus 11. And the units are such that we're going to cancel out everything besides, kilometers in the numerator. So SI units in, SI units out, we already took care of that. And then T is 86,400 seconds, and we got to square that. All right, so we know roughly that the mass of the Earth is 5.97 by 10 to the 24. But what exactly will these values give us, right? So we have to actually crunch the numbers. I'll show you that with the on-screen calculator for the benefit of posterity and all of our YouTube viewers. All right, where can we put this here? Right about there seems like a good spot for it. Clean that up a bit. All right, so let's click some buttons. 4 times I squared, there's pi squared, equals, so there's 4 pi squared, 39.47, times 4, 2, 3, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, right? 4.23 by 10 to the 7. Cubed. Okay, so there's my numerator. Divided by, parentheses, 6.67. That's the natural logarithm, I think, though. So this exponent, but I like to just type it in like this, times 10 to the negative 11. See that? So then I can see in parentheses, there's my 6.67 by 10 to the negative 11. It equals there. Yeah, if you like the E key or the exponent key, go for it. Divided by 86400 squared. Why is it the square root? I hit the wrong button. There you go, back. Back. Not divide by 0. Well, I wouldn't want you to. Great, here we go. Divided by 86400 squared. I think square root. Oh, I guess I thought that meant square root, but I guess I had it right the first time. My bad, everybody. Equals 6 times 10 to the 3, 6, 9, 12, 15, 18, 21, 24. 6 by 10 to the 24 kilograms. And remember, 5.97 by 10 to the 24 kilograms is sort of like a more precise value, but you know, they don't want students to just have this memorized and forego the calculation and just report that. So you got to show the working. And so these values lead to sort of this. More precisely, it leads to this answer. So if you got that in your calculator, you've done it exactly correct. 6.001, right? But we won't report it to sort of that level of significance. We just sort of round it to 6.0 times 10 to the 24. That's the mass of the planet that we're on.